Hi, we've got some more mole calculations, amounts of substance, past paper questions. These are taken from the OCR specification. It's on year 1 of the A-level chemistry course. So you need to know those equations. There might be some slight variations. You might use lowercase m for mass, but I use lowercase g to stipulate that it's mass in grams. You might see capital L for Avogadro's number, but I use L. Avogadro's number is 6.02 on the data sheet for OCR, or 6.022. Both of those times 10 to the minus 3. On the AQA spec, for OCR, it's on the data sheet. For AQA, it's given to you in the question, so basically just use what you're given. I have included ideal gas there. There's going to be another video on ideal gas on its own. But before you can really attempt mole questions, you need to know those equations off by heart, including the units, so you can recognise what you are being given in the question. Also goes without saying that you need to be able to convert between units such as grams and kilograms and decimeters cubed and meters cubed and centimeters cubed, etc. fluidly. So in terms of fluency, most of these questions on this video, with the exception of the last one, are multiple choice, which gives you an idea of just how quickly you need to be able to get to the answer in an exam. I've shown the working out, but obviously if you had an exam, you might be pushed for time. It's worthwhile being able to show you working out even at speed and under pressure. So we're going to work out the number of electrons we're given removed from that mass of neon atoms. So we've got a mass of neon atoms. We can work out from the data sheet the molar mass of neon atoms. So number of neon atoms is mass divided by molar mass. Number of electrons, well, electron is a particle, so we're going to have to use the equation has got a total number of particles in, capital N, and Avogadro's number. So yeah, the mass over molar mass there, if you look at your data sheet, the molar mass for neon is 20.2. Because every atom of neon loses 1 electron, the number of atoms is equivalent to the number of electrons removed. So it's going to be 1.00 times 10 to the minus 3 moles is the amount of substance. And if you multiply that by Avogadro's number, as I mentioned earlier, this was taken from an OCR past paper question, so you'd have to refer to your data sheet, and that would be 6.02 times 10 to the 23. Do you need a data sheet to work this out? Well, it's just that 6.02 times 10 to the 23 divided by 1,000. So we get to the answer as being 6.02 times 10 to the 20. Okay, so next up we've got a percentage yield question. To make things a little bit more simple for us, they've given us a balanced equation. Instead of working out the percentage yield though, the question has given us the percentage yield and we need to work backwards to get to the mass of silicon made. So the number of moles of silicon, we're going to probably need to use mass over molar mass. Then we need to work out the theoretical amount of silicon. That's in theory if there was 100% conversion. The actual amount of silicon in moles, and then the grams of silicon. So there's a few little prompts if you want to have a little go at this stage. So the amount of silicon tetrachloride is mass over molar mass. It's a 1-to-1 reaction, so the amount of silicon is equivalent to the amount of silicon tetrachloride. So yeah, going back to the first bit there, we've got 8.50 divided by 170.1, working out the molar mass third of SiCl4 is 170.1. Gives us 0.0500 moles. So they're being quite kind with the way that the numbers have worked out, because this is a multiple choice question. So because it's a 1-to-1 reaction, we've also got the amount of silicon that you would have theoretically. Actually though, we only achieved 90% of that, so the actual amount in moles is 90% of 0.0500. and then so the mass of silicon is equal to the number of moles times by the molar mass, which is going to be equal to 0.045 multiplied by 28.1, the molar mass of silicon, and that should work out to be 1.26 grams. Okay, so another number of particles question here, but this time we need to work out the number of hydrogen atoms in an amount of, that looks to me to be ethanol molecules, C2H5OH molecules. So the twist here is knowing that one molecule of ethanol contains, well, we'll see how we get on with the question. 6 moles of hydrogen per 1 mole of C2H5OH. So the number of atoms of hydrogen is going to be equal to the number of moles of the ethanol multiplied by 6, because that's the number of the amount of atoms of hydrogen multiplied by Avogadro's number. And again, I got that from the data sheet, 6.02 times 10 to the 23. It will be given to you in the question if it was AQA. Well, this is a little bit of a twist and one that catches a lot of students out. So we've got one molecule of a gas here, so we have got a number of particles, it's just that that number is 1. So we have got capital N in our equation, but whereas we're usually dealing with huge numbers for the number of particles, here we'll kind of turn this on its head a little bit, and we're going to deal with a single molecule at a very small mass. So there's a bit of a clue. We're going to be using that equation. From that we can then rearrange the number of moles as mass over molar mass and proceed from there. So rearranging the equation on the left there gives us the amount of substance in moles, and rearranging the equation on the right there gives us the molar mass is equal to the mass over the amount of substance. As I said before, the capital N is just going to be 1, and I've used the 6.02 times 10 to the 23 from the OCR datasheet. So that's given me the amount of substance in moles, or certainly can calculate it, there it is. And so now we plug that result into the formula on the right hand side to get to what the molar mass is. So the mass is given to us in the question in grams, and the amount of substance in moles we worked out in the first part on the left hand side there. That gives me a molar mass of 16.0 grams per mole, and that is only suitable for one molecule, or the molar mass rather, of methane. Okay, so next up we've got a reacting masses question linked to our knowledge of group 2. What do we need to know about group 2? Well, when group 2 metals react with chlorine, they make the metal chloride. Group 2 metals form 2+ ions, and chlorine is going to make the chloride 1- ion. So they will react together according to that kind of general equation there. We've got the mass of the metal, we've got the mass of the metal chloride, so we can work out the percentage of the metal in the chloride. The mass of the metal divided by the mass of the metal chloride times by 100 gives us 36.1%. So we can apply the same logic to figure out, well, what is the percentage of magnesium in magnesium chloride? What is the percentage of calcium in calcium chloride, etc.? So you can work those out, and there's the calculations if you want to try it. The answer is going to work out to be calcium. So 40.1 for the calcium divided by 40.1 plus 71.0, multiply that by 100, that gives you a percentage of 36.1. So yeah, it's not a common type of question, but that's how I went about doing it. So finally, a question which is not a multiple choice, and this one is a tough little question. A twist on water crystallization. Water crystallization is usually going to be an integer, but here we're asked to work out the value of x. That is the number of molecules of water of crystallization. We need to work that out to 2 decimal places. Okay. So if 13.4% of our methane hydrate is made up of methane, the rest of it must be made up of water. So in 100 grams of methane hydrate, we can work out the mass of the methane and the mass of the water. From those masses, we can work out the amount of substance in moles, because that's going to be mass divided by molar mass. And then from the ratio of those amounts, that's going to give us our value of x. So in 100 grams of methane, you would have 13.4 grams, so in 100 grams of methane hydrate, that is, you'd have 13.4 grams of methane and 86.6 grams of water. Looks like I've forgotten the units there. That would give me those amounts of substances in moles. Again, no units, very bad form indeed, not like me. And then to give our answers to 2 decimal places, make sure that you read the question and address the question. 4.811 divided by 0.8375 gives a ratio of 5.74 to 2 decimal places. So that would be the value of x to 2 decimal places.